welcome you all. In this today's session, let's discuss about the topic Boolean expression and logic gates. Boolean algebra and logic gates. The Boolean algebra was developed by the English mathematician George Boole in between 1815 to 1864. The Boolean algebra is described by only two logic functions, that is 0 and 1. It's also meant as true or false. The logic means it is a statement having two binary decision, true or false. So true is given by logic 1 and false statement is represented by logic 0. So it is used to perform the logic operation in a digital computer. So logic 1 represents a true value which is a high volt, and logic 0 represents false and logic 0. Logic operations are performed by the logic operators. The basic operators are AND, OR and NOT. AND is similar to that of logic multiplication, so that's why it is represented by a dot operator. Logic operator, the AND operation is performed by two literals, that is x and y, and the output is represented by x dot y. We are giving the two possible values. So here the total possible combination is represented by 2 power n, where n is the number of variables. Here x and y are the two variables. So 2 power 2 is equal to 4 combination. They are given as 0 0, 0 1, 1 0 and 1 1. Performing the dot operation, for 0 dot 0 the output will be 0. Similarly for 0 dot 1 and 1 dot 0 you will get the output as 0 itself, and for 1 dot 1 the output will be high. Since the logic operation A dot A is equal to A, and using the logic AND operator, the AND gate has been constructed with two input, with a basic of two input A and B, and output is represented by C. This is the logic symbol of a AND gate, followed by the truth table of AND gate with two input A and B and output C. So A dot B, output C is equal to A dot B. This is the truth table, and the Boolean expression for an AND gate, C is equal to A dot B. And the second type of operator is OR operator, which can be also said as logic addition, represented by the plus symbol. Similar to that of AND gate, it has a minimum of two input x and y. So combinations as earlier 0 0, 0 1, 1 0 and 1 1, and the output is x plus y. Logic addition. So if any one of the input is high, which makes the output high. Here for 0 0 the output is 0. For 0 1, 1 0 and 1 1 your output will be high. If any one of the input is high for an OR gate, the output will be high. So this is the OR gate symbol, followed by truth table and the Boolean expression of OR gate, where C is equal to A plus B, where A and B are the two input variables. And the third operator is NOT operator, which perform the logical negation of the input. So it is represented by a bar over the variable. If the input variable is represented by x, your output y is equal to x bar, the negation of the input. So here we are having a single variable as input. So 2 power 1, which is equal to 2 combination, that are 0 and 1. If the input is 0, your output will be high, and if the input is 1, your output will be low. So this is a symbol of a NOT gate, truth table of NOT gate, and the Boolean expression of NOT gate. Next, the explanation about the truth table. A truth table is a table that shows the all possible combination of input in a Boolean expression. Here it is represented as the number of possible combination is equal to 2 power n, where n is the number of variables used in the Boolean expression. This is a best example that shows the practical application of logic gate. Here we have to use an AND gate in order to activate a alarm. Here one of the switches, the two inputs, one of the switch is alarm switch and the other is person sensor. These are the two input given to the AND gate, and once a person go out of from home, we can switch on the alarm switch, which makes the input as 1, and the other input may be 0 or 1, which is represented or detected by the sensor. If there is no person intervene, the sensor output will be 0, and so the output of the AND gate will be 0, which turn off the alarm, that is the alarm will not be ring, and at the time when a person enters, the sensor detects and gives the input as 1, which makes both the input high for the AND gate, and the alarm will be activated. So this is a application of AND gate. And next, the application of an OR gate, which is given by the doorbell switch. Here we are having two input, which is given represented as a front doorbell switch and back doorbell switch. If any one of the switch is operated, the doorbell should ring. That way here, even if it is a front doorbell switch or it is the back doorbell switch, any one of the switch is activated or any one of the switch is made high, it should ring the bell. So this is the application of an OR gate. And the next type of gate is exclusive OR. Exclusive OR gate is a symbol of XOR gate and represented as Z. The output Z is equal to X XOR Y. Here also we are having two input variables. So the total combination is 4, 0 0, 0 1, 1 0 and 1 1. For an XOR gate, when odd number of input is high, it makes the output high. So for the combination 0 1 and 1 0, the number of input is odd, so the output will be high. For other two combinations such as 0 0 and 1 1, the output will be low, which is represented by a Boolean expression Z is equal to A bar B plus X bar Y plus X Y bar. This is represented as X XOR Y. And the negation of XOR gate is XNOR, represented by a bubble after the XOR gate, the representation of XNOR. Z is equal to negation of X XOR Y. The Boolean expression for an XNOR gate can be represented as Z is equal to X bar Y bar plus XY. For the 0 combination 0 0 and 1 1, your output is high, therefore it can be represented as X bar Y bar plus XY. And next, coming to the topic, universal gates. Among the type of gates, NAND gate and NOR gate are called as universal gates because any digital circuit can be implemented with these two gates such as NAND and NOR. So this is the representation or circuit symbol of a NAND gate, that is a bubble followed by an AND plus inverter is equal to NAND gate. So the truth table in which you are having the output C is equal to 1 1 1 0. Here when both the inputs are high, the output of AND gate will be 1, that is inversion, which makes the output 0. Inversion of AND is NAND. The output is 0 for the input combination 1 1, and for all other inputs such as 0 0, 0 1, 1 0, the output will be high. The expression is represented as C is equal to A dot B the whole bar. So this is the inverter symbol using NAND gate, and the second one is the AND representation using NAND, and the third one is the OR representation using NAND. It is called as universal gate because all other gates can be implemented using a single gate such as NAND or NOR gate. That's why NAND and NOR are called as universal gate. So this diagram represents the representation of inverter, the second one is AND, and the third one is OR gate. The second type of universal gate is NOR gate. So using this NOR gate also we can implement all other gates. And next is the basic theorems of Boolean algebra. So theorem 1 is properties of 0. So a literal a odd with 0 you will be getting a. If performed dot operator a dot 0 is equal to 0. And properties of 1 plus a is equal to 1 and 1 dot a is equal to a. Then commutative law, a plus b is equal to b plus a and then ab is equal to ba. That is associative law, a plus b plus c is equal to a plus b plus c. Performing the OR operation of a and b first, then ORing with c is equal to performing OR operation of b and c, then ORing with a. Similarly, with respect to dot operator, performing dot operation of a and b and then dot with c, that is equal to performing dot operation of bc and then dot with a. Distributive law is a into b plus c is equal to ab plus ac. It means that is a is distributed over b and c. So a dot b plus a dot c. Then a plus bc is equal to a plus b into a plus c. Then identity law or idempotence, a plus a is equal to a and a dot a is equal to a. The next is absorption law, a plus ab is equal to a, then a into a plus b is equal to a. Complementary law, then x plus x bar is equal to 1 and x dot x bar is equal to 0. And involution, it's double times complement, x double bar is equal to x. And next is De Morgan's theorem, which is the complement of sum is equal to product of its complement. And second De Morgan's theorem is complement of product is equal to sum of its complements. So this is what shown explained here. Theorem 1 of De Morgan's theorem is a dot b the whole bar is equal to a bar plus b bar. So it is obtained from the concept that NAND is equal to bubbled OR gate. NAND, the Boolean expression of NAND is a dot b the whole bar, that is equal to bubbled OR gate. So bubbled OR gate means inversion of it, that is a bar plus b bar. That is explained with respect to diagrams. The first one is the direct representation of NAND, where the inputs are a and b and your output y is equal to a dot b the whole bar. So since the NAND gate is equal to bubbled OR, here taking bubble, inversion of a and b with respect to bubble, which is given to OR gate, your output y is equal to a bar plus b bar. Y is equal to a bar plus b bar. So it is clear that ab the whole bar is equal to a bar plus b bar, which is the first De Morgan statement. The tableau proof of De Morgan's theorem, a and b are the input variables showing the combination 0 0, 0 1, 1 0 and 1 1. Taking the product of a and b by dot operator, a dot b is equal to 0 0 0 1 will be your output. Taking the inversion, you will get the output as 1 1 1 0, which represents the truth table of a NAND gate. And performing the inversion of a, will be obtaining a bar, which is 1 1 0 0, and next taking b bar, it is 1 0 1 0, and taking the summation, the logic OR operation of a bar and b bar, you get 1 1 1 0. Now comparing the third column and sixth column, the output will be proved, that is De Morgan's theorem is proved. A dot b the whole bar is equal to a bar plus b bar. The second De Morgan's statement, a plus b the whole bar is equal to a bar dot b bar. A plus b the whole bar is equal to a bar dot b bar, which is equal to a plus b the whole bar can be obtained using a NOR gate. Y is equal to a plus b the whole bar, that is equal to NOR gate is equal to bubbled AND. So a bar into b bar, a plus b the whole bar is equal to a bar into b bar. This is the proof of second statement of De Morgan's theorem. A plus b the whole bar, the third column represents the output a plus b the whole bar, which is NOR, that is equal to last sixth column a bar into b bar. So both are same. It has been proved.